Hello everyone, welcome to my video on trigonometric substitution for indefinite integrals. So in the previous video we saw trigonometric integration, which is not the same thing. This is a substitution. Well, it's not really a substitution, it's an inverse substitution. And we're going to see that when we solve trigonometric substitution problems, we eventually reduce it down to a problem which may require trigonometric integration. Okay, so make sure you're comfortable with that. Go look at my other video and before you start this one. Now, in this case here, what you have to do is you have to identify the type of integral. You have to look at its form. So this is what's really important. So looking at the strategy over here, if the integral is of the form a square root of a squared minus x squared dx, a is just a number. You have a number squared minus x squared. And the other thing I want to mention, it doesn't necessarily have to be a square root. It could be 3/2. Like if you think of a square root as exponent 1/2, well, you could deal with something that has exponent 3/2, 5/2, 7/2, so on and so forth. But essentially, if you have a square root with a squared minus x squared, so a number squared minus x squared, we are going to use the substitution or the inverse substitution, x equals a times sine theta. Okay. In order to solve this problem, you use this. So a way that I remember it is a squared minus x squared. I could think of it as 1 minus, let's say, cos squared, because we want to take the square root, right? Right now, in this case, we cannot take the square root because we have a minus or an addition in between two terms. You cannot take the square root of each term individually. This is really important. That's a common mistake that students make. If it's a multiplication, then you could take the square root of each term individually, but with a minus or an addition sign, you cannot. Okay, so keep that in mind. So we want to transform this. How do we transform it? Well, we're using this property over here. The fact that sine squared plus cos squared equals 1, well, if we move the cos squared, let's say, over, we have 1 minus cos squared or 1 minus something squared. Maybe let's do it with sine. It doesn't matter which one, you're going to have to, it depends on the problem. But let's just put sine for the fun of it. 1 minus sine squared, if I bring the sine squared over, that's just equal to cos squared. Alright, so we went from something, a number minus something squared, and we transformed it to something squared. Cos squared now on its own, we could take the square root of this term. 1 minus sine squared, we cannot take the square as the square root, but transforming it using this identity, we can now take the square root of cos squared because it's just going to cancel the exponent. Okay, and that's the idea behind solving trig substitution problems. Okay, so if we have specifically the case a number squared minus x squared, we're going to use the substitution x equals a sine theta. Next, what we have here is if instead of a minus now we have a number squared plus x squared inside a root, now we're going to use tan. Why? Why are we using tan? Well, the fact that we could use the property that 1 plus tan squared is equal to secant squared. So something squared, which you can think of 1 as 1 squared, something squared plus tan squared, transforming it to secant squared, we can now take the square root of this term. We're going to be just left with secant, right? So this is the idea. So whenever you have a number squared plus x squared, we're using the substitution tan. The last case that we have is if it's x squared plus a squared or a squared plus x squared, it doesn't matter which first, it's commutative. So this, you could switch them and it doesn't matter. Here for subtraction, you cannot switch them. A squared minus x squared is not the same as case 3, x squared minus a squared. Okay, so here we're subtracting x squared minus a squared, so the numbers after. And in this case, we have to use a substitution with secant, and we're going to apply the property that secant squared minus 1, something squared minus a number squared is equal to tan squared. Okay, so these have to be memorized. If you have to, write them all down. And we're going to use this to solve a couple of problems. So let's go ahead and take a look at a couple of examples. So in our first example over here, it says to evaluate the integral x times the square root of 1 minus x squared dx. So this is a trigonometric substitution problem, but this is my advice. If it says to evaluate and it doesn't specify how, in this case here, before I do a trig substitution, I'm doing a u substitution. You could get this with just a regular u substitution, letting u equal 1 minus x squared. The derivative is negative 2x, and notice that the x is going to cancel with the x that's sitting in the front of it. So if you could get it with a regular u substitution and you don't have to use a trig substitution, that's my advice. Go ahead and solve it this way easier. But let's pretend, just for the sake of argument, that your teacher forces you. They state specifically, evaluate this integral using a trigonometric substitution. Well, if we're forced into it, now we have to figure out what case are we dealing with here. So looking at the integral, we have 1 minus x squared, which we could think of as the integral of x. 1 is 1 squared, so something squared, minus x squared dx. Okay. Since we have a number squared minus x squared, this was case 1. So we have to apply the substitution x equals a sine theta. Okay, so, or the inverse substitution I should say. In this case, the a is this piece here. This is the a. So we're going to let a, I'm not going to write a, let's write a 1, because a is 1, times sine theta. This is the substitution that's going to work in here. Let's go ahead and see why. So after you find x, so we're going to transform everything in terms of theta. So let's take the derivative of x. So taking the derivative, we get derivative of sine is cos theta, d theta. And now we substitute everything we know into here. So this is like side work. We get the integral. Instead of x, x is equal to sine theta. So we're going to transform it. Inside the root, we have 1 squared, which I'll just leave it as 1 for now, minus x squared. But x, we're substituting it with sine. So it's 1 minus sine squared theta. Okay. And dx, we're going to substitute it using our derivative. When we took the derivative, it's equal to cos theta d theta. So I don't have space, but this is on the outside of the bracket, we have cos theta d theta. So we transformed everything in terms of theta now. Okay, so there's no x's involved in here. Okay. And now we're going to apply the property that we know, sine squared theta plus cos squared theta equals 1, and we want 1 minus sine squared. So we're going to bring the sine squared over, giving us cos squared theta equals 1 minus sine squared theta. So I'm going to substitute the 1 minus sine squared theta inside the root and rewrite it as cos squared theta. So we have the integral. I have the sine here and the cos here. This is not a division, it's all multiplication. I just didn't have space to write it on one line, but imagine this on one line. So I'm just going to put them together. Sine theta times cos theta. Inside the root, I'm going to rewrite 1 minus sine squared theta as cos squared theta. And we're left with d theta. So that's applying the property. And we know the square root of cos squared just cancels each other. We're left with just cos. So we have sine theta times, here we have square root of cos squared is cos, and then we have another cos over here. So this is times cos squared theta, d theta. Okay. So we went from a trig substitution and we transformed it to sine times cos squared, which is now just a trig integral. We have to solve this using our trig integrals. We have sine times cos, so we have to look at the exponents. Since the exponent of the sine is odd, we have to remember we have to let u equal cos. That's from our previous video, so go ahead and make sure you remember that. So we're going to use the substitution u equals cos theta, take the derivative, and we get the derivative of cos is negative sine theta d theta. And now we're going to transform this using just a regular u substitution. So sine theta stays, the cos gets transformed into u, so we get u squared. Oops, sorry, not d theta. I wrote it twice. Sorry about that. There's supposed to be 1 d theta. Integral sine stays, cos squared gets transformed into a u squared, and d theta, solving it for here, we're going to divide by negative sine. We get du over negative sine theta. The sine thetas cancel, which is great. We're just left with the integral. The negative, I'm going to pull it on the outside, and we have the integral of u squared du. The integral of u squared is just u cubed. We have the minus in the front divided by 3 plus c. And now this is the issue. So remember when I said you start in terms of x, you have to finish in terms of x? Same thing applies. But this is a bit more difficult. From u, we could go back to theta using this. So this is equal to negative cos cubed theta over 3 plus c. And you still can't leave it like this. You can't leave it in terms of theta. We started in terms of x. We have to come back in terms of x. How do we transform cos cubed theta over 3 back in terms of x? Well, you're probably thinking, well, just go back to the first substitution that we did. Well, remember, it's not a substitution, it's an inverse substitution. And the substitution we used was x equals sine theta. 1 times sine theta or just sine theta. We don't have cos. If you can't use the derivative, if you're thinking of using this formula, that's just going to get complicated. But what we do use over here is we go back to our secondary foreknowledge and we create a right triangle. Okay, so we're going to have to use our trig properties. So we use our original substitution to create a 90-degree triangle. This is our 90-degree triangle. And we're going to use this substitution here. So we know that if I divide by 1, you don't have to do it like this, but you could write it this way. X over 1 is equal to sine theta, right? So I divided it by 1. And we know from high school our trig formula, SOHCAHTOA. So sine theta could be expressed as the opposite over the hypotenuse. This is the opposite. It's opposite over divided by hypotenuse. Okay. From secondary 4 math. So we have to apply it here. Let's call this angle theta. So you can use any angle as theta. It's already up to you, except the 90 degree. You cannot use the 90 degree. So let's call this angle here theta. So if this is the angle theta, my opposite side is here, opposite to this angle. So this is the opposite side. The hypotenuse is always across the 90 degree. This is the longest side. So we call this the hypotenuse. And based off our substitution, our initial substitution that we used, we have x over 1. So x is the opposite. So this side we call x, and the hypotenuse is 1. Okay. We have two sides of a 90-degree triangle. Let's go find a third. How do we do that? Yes, Pythagorean Theorem is back. So back from secondary 3 math, we have to use Pythagorean Theorem. C squared equals a squared plus b squared. C is the hypotenuse, the longest side, in this case 1. 1 squared equals a. A is one of the legs. It doesn't matter which one you choose. I'm going to take x squared plus, and b squared is what we're looking for. We're looking for the other leg. I'm calling this a. I'll call this b. Solving for b, we bring the x over. We get 1 squared, which is 1, minus x squared equals b squared. And solving for b, we square root both sides. 1 minus x squared equals b. Okay. So the missing side here is square root of 1 minus x squared. This is the adjacent side. Adjacent meaning touching, which is the angle, sorry, what's the side that's touching this angle? Square root of 1 minus x squared. So the adjacent is reserved for the side that's touching the angle, which is not the hypotenuse. So the hypotenuse is touching this angle as well, but this is always hypotenuse because it's across the 90 degree. Okay, it's along this side. So this is the other side that touches our angle. And notice that a way you could check if you're doing this correctly is whenever you solve for that missing side, you always get the initial piece of the problem. This was given. Okay. So this is what we have here. Okay. If you don't have the same thing, what you started with, you made a mistake, go back and check your work. Okay. So why do we set up this triangle? Why do we create this 90-degree triangle here? Well, we're trying to figure out what cos is equal to. Now that we have our 90-degree triangle, we can find what cos is. Let me just give some room. This implies that cos theta, we know from, again, SOHCAHTOA, our trig knowledge, it's adjacent over hypotenuse. A over h. Well, now we know that the adjacent is square root of 1 minus x squared, and the hypotenuse is 1, so divided by 1. So cos theta can be expressed as the square root of 1 minus x squared. So that means this piece here, if we want to go back in terms of x, is really equal to negative, I'm going to put in bracket, cos theta, cos cubed theta. Again, you could think of cos cubed theta as cos of theta, all that cubed. Same thing, it's just notation. So we could think of this as negative divided by 3. The cos theta is really just square root of 1 minus x squared, all that cubed plus c. And this is the actual answer written in terms of x. Okay. So we use our original substitution, our inverse substitution, to create a 90-degree triangle. With the 90-degree triangle, go get the terms that are given here and express them solely in terms of x. Okay. So this is the answer for the first problem, and we're done. Let's take a look at another example. So in the following example over here, we have to evaluate the integral of 1 over x squared times the square root of 4x squared minus 1, all that dx. So the first thing to notice is that a u substitution would not work here. So if you let u equal 4x squared minus 1, it won't cancel out with the x squared on the outside, so u substitution doesn't work, but it should be your first instinct before you try a trig substitution. But in this case, we have no choice. A trig substitution is the way to go. The other thing you have to notice, it's not the same as the first example that we saw, because the first example is 1 minus something squared, whereas here we have something squared minus 1. It's the reverse order. So we're not dealing with sign, we're using the trig substitution, where x equals secant in this case. This is our third case. Okay, so always identify and analyze the form before you start solving. Okay, so in this case here, it's secant, but the only thing that's weird is that we have this 4 in the front. Let's go ahead and get rid of it, because we want x squared alone minus a number squared. Getting rid of the 4, what we could do is factor out a 4 from the bottom. We have 1 over x squared, square root of 4, x squared minus a quarter dx. How did I get a quarter? Well, factoring out a 4 is the same as dividing by 4. And if you don't believe me, take the 4 in this case and distribute it back in. 4 times x squared is 4x squared, and 4 times negative a quarter is minus 1. So in this case, it works. Okay, so I'm just going to remove the 4, the root 4 as a 2, and put it in front of the equal signs. So we have 1/2 on the outside, because the root 4 came out as a 2, and it's on the denominator, so it's a half. We still have the 1 over x squared, and inside the root we're left with x squared minus a quarter dx. Okay, but we don't want a quarter. We want to write it as x squared minus a number squared. How can I rewrite a quarter as a number squared? Well, notice that a quarter is simply just 1 over 2, all that squared, right? If you square a 1, you get 1. If you square a 2, you get 4. So this, I could write it as a half squared. Why do I want to do this? Well, now it identified what my a is. Now I know my a is a half, okay, written in this form. So a bit of manipulation just to figure out what the a is. And now we use our substitution, or inverse substitution. X equals a times sine theta. So in this case, a is a half, and we're gonna, no, not sine theta, sorry, secant theta. You don't want to make that wrong substitution in the beginning, because then the rest is going to be wrong. And now we take the derivative with respect to theta. So the derivative of secant is secant tan theta d theta. And now we transform everything that has x's in terms of just thetas. So we have the 1/2 that's sitting in the front, integral. I'm going to start off with the dx on the numerator. So dx is just this whole thing. So I'm just going to recopy it. 1/2 secant theta tan theta d theta, all on top, divided by. On the bottom we have x squared, so x is equal to a half secant theta. So x squared is equal to secant squared theta over 4, because I'm squaring both sides. So secant times secant is secant squared, and a half times a half is a quarter. And inside the root, what we have is the negative 1/2 squared. I can't do anything. And the x squared, again, is the same thing. We have secant squared theta over 4 minus a half squared, which I could write as minus a quarter. Okay, so a lot going on here. Let's deal with it step by step, but notice that there's no x's anymore. We expressed everything solely in terms of theta. Okay, even the dx was transformed in terms of theta. Okay, so now what we could do is focus inside the root. Inside the root, I could factor out a quarter, leaving me with secant squared theta minus 1. This is what I want. The secant squared theta minus 1 is the property we knew we would have to apply at some point. So rewriting secant squared theta minus 1, I could write this as a quarter times secant squared minus 1 is just tan squared theta. Okay, and square rooting all this is all the same. The square root of a quarter is a half, because of a half times a half is a quarter, and the square root of tan squared is just tan. So everything inside the root is just a half tan theta. So let's go ahead and write that. I'm just going to erase this to give myself some room, but I'll leave the original substitution. So keep this in mind. We're going to use it again. So what we have is the 1/2 in the front. We have the 1/2 on top, which we could take out as a quarter, and then we have a division of a quarter. I'm going to take that out as well. So we have a half times a half, which is a quarter, divided by a quarter. That's just going to cancel. On top we have secant theta tan theta d theta and on the bottom the quarter I took out, and we're left with secant squared theta. And we said that the square root of all this is the same as just a half tan theta. Yeah, a half tan theta. Okay, so we have to be careful with all these constants and not lose track of what's going on. So the quarters cancel here, you're left with 1, and then you're dividing by a half. So whenever you divide by half, it's the same as multiplying by 2. So since these guys cancel and this half multiplies, we're dividing by the reciprocal. We're multiplying by the reciprocal. So we could just hit the 2 in the front. One of these secants cancels with one of these, and one of the tans cancels with one here. This half, I multiplied it by 2, and we're left with just a secant on the bottom. So we're left with 1 over secant theta d theta. We have to integrate this, and this looks very difficult, but it's actually not if you know your properties. What's 1 over secant equal to? Well, we know this is just 2 integral of cos theta. 1 over secant is just cos, and this is very easy to integrate. We know the integral of cos is just sine. So this is 2 sine theta plus c. Okay. But the issue is, once you have this expressed in terms of theta, we're not done. We have to go back in terms of x. We start in terms of x, we finish in terms of x. We cannot use this. So what do we have to do? We have to go ahead and create our triangle. Let me make some room and do that. Okay. So we want sine theta. What do we know? We know secant theta. So solving for this, this is the substitution that we started with. I'm going to multiply the 2 up here, so we have 2x over 1 equals secant theta. I'm essentially cross multiplying. And secant theta, we just saw, is the same thing as writing 1 over cos theta. Okay. And now cos theta is just, what we could do is kind of ignore the secant for now and look at this piece and this piece and cross multiply. We're essentially cross multiplying here, giving us cos theta times 2x equals 1 times 1. So cos theta was multiplied up here, 1 was multiplied up here, and next I'm doing cos theta is equal to 1, and I'm going to divide the 2x over. Okay, so I had secant, I rewrote secant as 1 over cos, and then I just took the reciprocal. If 2x over 1 is equal to 1 over cos, if we flip both sides, that means cos is equal to, instead of 2x over 1, reciprocal, 1 over 2x. It's essentially just cross multiplication. So cos theta is equal to 1 over 2x. Why do I want cos theta? Well, going back to our trig ratios, we know cos theta is equal to adjacent over hypotenuse. So katoa. And we're going to use our original substitution. I'm just switching the secant in terms of cos so that I can set up my triangle. So I always take my theta to be this angle. This is 90 degrees. If this is the angle that I'm working with, my adjacent side, this is the hypotenuse. The longest side is always across the 90. This makes this the adjacent, and this would be the opposite. So the adjacent side is 1, and the hypotenuse is 2x. Now we use Pythagorean Theorem to go find the missing side, the opposite side. So let's go ahead and do that. I gave you guys a trick earlier. You know what the answer should be. You should always get back what you start with. But don't just assume it. Like, you should actually solve it using Pythagorean Theorem. So let's go ahead and do that. I'm just going to erase this and give myself some room. So we know c squared equals a squared plus b squared. So c squared in this case is 2x squared equals a squared. I'm going to call this a, 1 squared. And we're looking for b. I'm calling this side b. Doesn't matter what you call a and b. So this is 4x squared equals 1 plus b squared. The 1 we move over, so we subtract 1 over. So it's minus 1 equals b squared. And then lastly, to solve for b, we take the square root on both sides. 4x squared minus 1 equals b. Is that the same what I have here? Yes, so I know I'm doing this correctly. Okay. And why did we want this? Well, the question that we're looking for is this. We're looking for 2 sine theta. We want sine theta. Well, let me erase this. Sine theta, again from our trig ratios, we know sine theta is equal to opposite over hypotenuse. So we need the opposite side over the hypotenuse. In this case, the opposite is the square root of 4x squared minus 1, and the hypotenuse is 2x. So now we have a relationship between sine theta and x. So we're going to express this as the final answer is actually 2 times, instead of sine theta, we're going to write this thing. Square root of 4x squared minus 1 over 2x plus c. And the 2's cancel. 2 divided by 2 is 1, so don't leave that. And this is in fact the final answer. Okay. Let's take a look at our final example. So let's take a look at our final example. Example 3 says to evaluate the integral of dx over square root of x squared minus 6x plus 13. But wait. This does not look like it's in the form of the first 3 that we saw in our strategy. How do we deal with this? We have x squared minus 6x plus 13 underneath the root. We want something squared plus or minus a number squared. Well, the trick for these types of problems is if you're ever given a trinomial and you want essentially a binomial or 2 terms separated by a minus or an addition, what we have to do is we have to complete the squares. So we saw this in high school, but it comes back. Method of completing the squares. Let's go ahead and do that. So recall, how do we complete the squares? The key aspect you have to remember is b over 2 all that squared. Okay. There's different variations of this, but b over 2 squared should work. You might have to factor out, if there's a constant in front of your x squared, you're going to have to factor it out. You want to ensure that what's in front of the x squared is a 1. If not, the rule becomes b over 2a all that squared. But either way, the way I do it is I ensure that in front of my x squared I have a 1. If there's not a 1 here, I factor that number out and I work with fractions. And I still use this property. So this is our key property, our key value. Okay, we'll see why it's super important in just a moment. But remember, when we're given polynomials, quadratics especially, it's of the form ax squared plus bx plus c. Think of it like this. So here our a is 1. The constant in front of the x squared, or the coefficient in front of the x squared I should say, is 1. The coefficient in front of our linear term, the x, is not 6 but negative 6. And the constant, the value that's all alone here, is 13. Okay, so we're thinking of it in this form. And what we do now, we're going to complete the square. So we have it in general form and we're going to switch it to standard form or factored form. Not factored form, standard form or vertex form. So if you remember from high school, it's a x minus h squared plus k. We want to package it up so that we have something squared. This is the idea of completing the square. So we have it in general form, we're going to switch it to this form. We're going to package it up. So the idea is you have x squared minus 6x plus 13. And that's equal to x squared. We're going to leave this and we're going to plug in to our key value here. What's our b? We've established that the b is negative 6. Let's plug it into this. We get negative 6 divided by 2, all that squared. Negative 6 divided by 2 is negative 3, all that squared. And negative 3 squared is 9. 9 is the magic number. What are we going to do? Well, with 9, I'm going to use a different variable. We're going to minus 6. This is equal to x squared minus 6x plus 13 is equal to x squared minus 6 plus 9. You always do the addition first. Minus 9 plus 13. Okay. Notice this is the exact same thing because I did not change the value. I added in 9, I subtracted out 9. So this is a fancy way of adding 0. Why do we do this though? Well, we focus on the first 3 terms. If we focus on the first 3 terms, and you always put the addition first, you could package this up nicely. You could use a product sum method or M&N method to figure this out, but essentially what you get is x minus 3 squared. Okay, so 2 numbers that multiply to 9 and add to negative 6, that would be negative 3 and negative 3. Okay, or another way of catching this is that right before the last, this is why I show all my work here, it's always going to be the value right before you get the magic number. Okay, so the value that's here is always going to be this value here right before you squared it. Okay, so negative 3. And then the last 2 terms that we have is negative 9 plus 13, which gives us plus 4. And now we have something squared plus a number. Okay, so we're gonna rewrite what's in the bracket as this, and now we could use our trigonometric substitution. Okay, so this is equal to the integral of dx. Underneath the root we have x minus 3, we have something squared plus 4. But this is still not good enough. We completed the squared, it's great. It's almost of the form, but not quite. What we have to do now is apply a u substitution, because we want x squared or something squared, not a binomial x minus 3 squared. So to get rid of that, every time you use a complete the squares argument, it's followed by a u substitution. And we're going to let u equal what's in the bracket. U equals x minus 3. That means du equals dx. So this thing here is equal to dx is being replaced with du. And we have the integral, sorry, we have the square root of u squared plus 4. And now we're set to go. Now this is exactly what we wanted. This is case 2. Okay. So instead of x, we're just using the letter u. Okay, so now we're using our inverse substitution. Since it's a plus, and 4 we could think of 4 as 2 squared, we have x squared, in this case u squared plus a number squared. And since it's a plus, our u is going to be equal to tan. And our a is the value that's here. So we're using 2 tan theta. If we take the derivative of u, instead of x, we're using u now. The derivative of tan is secant squared theta d theta. Now we're going to substitute all the u's in terms of theta. So this is equal to the integral du on the numerator is just 2 secant squared theta d theta. And inside the root, we're rewriting the u as 2 tan theta. 2 tan theta, all that squared, plus 2 squared, which is 4. Okay. Notice that 2 tan theta squared is the same as 4 tan squared theta. And again here, we could factor out a 4. If we focus underneath the root, we have a 4. This is tan squared theta plus 1. And we know this. Tan squared theta plus 1 is just, this is equal to 4 secant squared theta, which is simply just 2 secant theta. So if we focus just on the root, we have 2 secant theta. So let me erase this piece. I'm going to keep our substitution. And we're going to rewrite this as 2 secant squared on top, d theta. And on the bottom, the root turns into 2 secant theta. Okay. The 2's cancel. One of the secants cancels, leaving us with the integral of secant theta d theta. Okay. This one, unfortunately, is a lot more difficult to solve because secant could be rewritten as 1 over cos, but then to integrate 1 over cos, we can't do. So how do we integrate secant? We actually saw this in the previous video, in our trig integrals video. The integral of secant, I'm not going to reprove it, we just have it memorized, is ln of secant theta plus tan theta plus our constant. Okay, so this we actually proved. You multiply the top and the bottom by secant plus tan, and you get it with a u substitution. But since it was done already in a previous video, I'm just going to write the answer. This is equal to ln of secant theta plus tan theta. Again, we start in terms of x, we finish in terms of x. How do we do that? Well, we use our original substitution and create a 90-degree triangle. Let's go and do that. So here's my 90-degree triangle, and now we're using it with tan. So we could write tan theta divided by 2 as u over 2. And from our trig knowledge, we know that tan is equal to opposite over adjacent. So the opposite side is u. So if I take this angle here, this is my opposite side. As always, the side opposite to the 90 degrees is the hypotenuse, the longest side, and that leaves us with the bottom as the adjacent side. So in this case here, my opposite side to the angle that I chose is u over here, and the adjacent side would be on the bottom here too. okay, we have to go find the hypotenuse. How do we do that? Pythagorean Theorem. C squared equals a squared plus b squared. We should already have an idea of what we expect our answer to be. But let's go ahead and solve it. We're looking for the longest side, the c. That's the hypotenuse. A squared is u squared plus 2 squared. Square root both sides, we get square root of u squared. 2 squared is just 4. So it's the square root of u squared plus 4. Is this correct? Let's go ahead and check. Is that what's sitting up here? Yeah. It's not exactly in the form of what we started up here, but we transformed it into this stage here, which is square root of u squared plus 4 in terms of u. And that's what we have here. 2 squared is 4. So this is good. And now we could answer this part. We could transform it now that we created our triangle. But what's difficult about this piece is that we have to get a secant and a tan. Well, tan's not an issue. Tan we know is equal to u over 2, so we could express it in terms of u. So this piece is okay. It's the secant that's the issue. How do we deal with secant? Well, from the triangle we just created, secant we know using our properties is 1 over cos theta. And we know cos theta is adjacent over hypotenuse. If you know the property that secant is hypotenuse over adjacent, you can use that in one shot as well. But I usually do it in this step. It's an extra step, but I think it's easier. And cos we know is adjacent over hypotenuse, so in this case the adjacent is 2 and the hypotenuse is square root of u squared plus 4. And since you can think of this as a fraction divided by a fraction, so you have a fraction on top, you have a fraction on the bottom, we multiply by the reciprocal. So we're just gonna flip the second fraction. So 1 over 1, which is just 1 times square root of u squared plus 4 over 2. So secant theta is just equal to square root of u squared plus 4, all that divided by 2. And now we could write this integral here. This is all side work. Now I'm continuing at this stage. We have ln secant. We just showed secant is equal to this. So square root of u squared plus 4, all that divided by 2, plus tan theta we know is u over 2. So plus u over 2 plus c. Okay. So we used our triangle to express this integral in terms of theta back in terms of u. Okay. If you're thinking we're done here, that's incorrect, because again, we started in terms of x. Your job is to finish in terms of x, not in terms of u. So there's still a bit of work to do. I don't have much room, so I'm just going to write it on this stage. We have to go back to our initial substitution, right? We started off with a u substitution. We let u equal x minus 3. So replace your u's back as x minus 3. So we have the square root of x minus 3 squared plus 4 underneath the root plus u, it's all over 2, so I'll put the whole thing over 2. And we know u is x minus 3. Plus our constant because it's indefinite. And this is in fact the final answer. Okay, so very difficult. Trigonometric substitution requires practice. Make sure you're accustomed to creating your triangle whenever you have an indefinite integral. With trig substitution, you're always creating these triangles here. Okay, so make sure you always come back. You start in terms of x, you come back in terms of x. Okay, so I hope this video helped, and keep practicing. I'll see you in the next one.